Hi everyone. So today we're going to discuss another essential topic in geotechnical engineering, particularly in foundation engineering, which is all about the compressibility of soils. So in order for us to understand more of compressibility, we need to first know why is it happening? So why does the soil compresses or why does it settles? So in this introduction, we need to first know why the causes of compression. So first, the soil compresses or it settles because of the deformation of soil particles. When an additional load is applied to a soil profile, it causes the soil particles to be deformed, therefore compression occurs or settlement occurs. So kapag na-deform yung ating soil particles, so pwede siyang lumiit and therefore compression occurs. And also, because there is a relocation of soil particles, compression also occurs. So kapag ang additional load natin i-apply natin sa lupa natin. So, nadi-disturb yung ating lupa and therefore, the relocation of soil particles occur and then afterwards, decompression happens. And lastly, the expulsion of water or air from the void spaces because when an additional load is applied, so the tendency of the water is to expulse or the air is to expulse from the void spaces. Therefore, if the water expulses, the void spaces will be lessened and therefore the compression will occur or the settlement will occur. Okay? So, what are the categories of soil settlement? Number one is what we call the elastic settlement or the immediate settlement. So this is the first settlement that occurs right after the load is being applied to soil. So it is caused by the elastic deformation of dry soil and of moist and saturated soils without any change in the moisture content. So elastic settlement calculations generally are based on equations derived from the theory of elasticity because we know that the foundation is elastic. So elastic settlement or immediate settlement occurs due to the application of the load. And then number two is due to number two category of soil settlement is what we call the primary consolidation settlement. So it is the result of a volume change in saturated cohesive soils because of expulsion of the water that occupies the void spaces. So primary consolidation settlement is the most common settlement that occurs in a soil profile or after a load is being applied. So elastic settlement may not occur right after the application of load and but primary consolidation settlement will really occur. And then lastly is what we call the secondary consolidation settlement. So it's observed in saturated cohesive soils and organic soil and is the result of the elastic adjustment of soil fabrics. It is an additional form of compression that occurs at constant effective stress. So, if the primary consolidation settlement is due to volume change in saturated cohesive soils, the secondary consolidation settlement is because of the elastic adjustment of soil fabrics. So, it occurs in a very cohesive soils. So, secondary settlement may not also occur after primary consolidation settlement if the soil is not that very cohesive. And then take note class that if you are to determine settlement, the only type of soil that settles is clay. So, soil like gravel, sand, and silt is not settling. But it will settle if it is with combination with clay. So the main cause of settlement will always be clay. So the consolidation settlement is the sum of the T settlement. So total settlement of a foundation can be given as S sub D equals S sub C plus S sub S plus S sub E, where S sub D is the total settlement, S sub C is the primary consolidation settlement, S sub S is the secondary consolidation settlement, and S sub A is the elastic settlement. So the total settlement may just be primary consolidation settlement or primary consolidation settlement plus the secondary consolidation settlement, or it can just be the elastic settlement plus the primary consolidation settlement, or lastly, it will be the sum of the three, which is the primary consolidation settlement plus the secondary consolidation settlement plus the elastic settlement. So this is what happens when there is consolidation settlement. So this is the original height of the soil, and when load is applied, so this is the original height of the soil, and when load is applied, the soil is being compressed, the soil will settle, and there will be change in the height of the soil, and this will be the difference of the height of the soil from the original height to the second height after the settlement of soil. So if you may ask, what is the difference between consolidation and compaction? So compaction is immediate. Uh, it is being done after, in order for us to avoid settlement of the soil. So consolidation settlement is time. It takes time rather. So it is very long process. It takes years for consolidation settlement to occur, but compaction is just days or it could be months, but no, just days. So compaction is very much done in order for us to avoid settlement of the soil. In the laboratory, we have what we call one-dimensional laboratory consolidation test, and it is used in order to determine the consolidation of a certain soil sample. So the one-dimensional consolidation testing procedure was first suggested by Carl Tersagi, and this test is performed in a consolidometer, or usually referred to as an odometer. So this is an example of an odometer, and the soil specimen is placed inside a metal ring with porous stones, one at the top. So these are the porous stones, one at the top and another at the bottom. The specimens are usually 64 mm in diameter and 25 millimeters thick. The load on the specimen is applied through a level arm, and the compression is measured by a micrometer dial gauge. The specimen is kept underwater during the test, and each load is kept for 24 hours. After that, the load usually is doubled, which doubles the pressure on the specimen, and the compression measurement is continued. At the end of the test, the dry weight of the test specimen is determined. So, this is an example of a consolidometer, and if you look at this one, this is where the soil sample is put, and this is the dial gauge. And then there is time deformation plot during consolidation for a given load increment. So in stage 1, this is the initial compression, and stage 2 is the primary consolidation, and stage 3 is the secondary consolidation. So the stages of consolidation in an odometer or consolidometer is shown in here. So stage 1 is the initial compression, which is mostly caused by preloading in the consolidometer. And then stage 2 is the primary consolidation, during which excess pore water pressure gradually is transferred into effective stress because of the expulsion of pore water. And stage 3 is the secondary consolidation, which occurs after complete dissipation of excess for water pressure when some deformation of the specimen takes place because of the plastic readjustment of soil fabric. So let us further discuss the three types of settlement. So number one settlement is what we call the elastic settlement. So in elastic settlement, we have to consider two types of foundation, the rigid foundation and the flexible foundation. So the elastic settlement is equal to C sub S QB multiplied by 1 minus mu squared over E sub S, or equal to QB multiplied by 1 minus mu squared over E sub S multiplied by I sub B, where C sub S is the shape and foundation rigidity factor. It is a constant in foundation. And B is the width of foundation or the diameter if it's a circular foundation. And then Q is the force over area or the net vertical pressure applied. And mu is the Poisson's ratio of the soil, which is also constant in every type of the soil. And E sub S is modulus of elasticity of soil, also constant, depending on the type of the soil. And lastly, I sub B or influence factor also depends on the type of soil. So let us look at this sample problem. How do we solve for the elastic settlement in a foundation? So a rigid column footing 1.2 meter in diameter is constructed on unsaturated clay layer. So the load on the footing is 170 kilonewton, and we have to estimate the immediate settlement or the elastic settlement of the soil and assume that the clay has modulus of elasticity equal to 6,900 kPa, Poisson's ratio equals zero point 0.2, and IP or influence factor equals 0.79. Take note, class, that in other books or other authors, they denote the influence factor as I sub F. And then, how are we going to solve for the problem? We need to first know the formula for the elastic settlement. Again, it's equal to QB multiplied by 1 minus mu squared over E sub S multiplied by I sub B. Why did it happen that C sub S is not given? So we have uh, to consider the given in this problem. That's why we use this formula. Given is influence factor and not C sub S. So we have to first determine what is Q, the vertical pressure applied. So in this problem, the only given is the force. It's 170 kilonewton. That's the load applied on the soil. But we can solve for Q. But we can solve for Q as we all know that Q is equal to Q over A or P over A or the force over the area of the foundation. So the force is equal to 170 kilonewton all over the area of the foundation. It's a circular footing with given diameter. So pi over 4 times 1.2 meter squared. Q will be equal to 150.31 kPa. So Q is already solved. B is given. So B is either width or diameter of the footing. So in this case, it is a circular footing. So we have to consider the diameter of the footing, which is 1.2 meters. And then we have given value of Poisson's ratio, which is zero point 0.2, and modulus of elasticity, which is 6,900 kPa, and influence factor, which is equal to 0.79. We just have to substitute the values in the formula. So this gives us 150.31 multiplied by 1.2 multiplied by 1 minus zero point 0.2 squared over 6,900 multiplied by 0.79, we are given the value of the elastic settlement of the soil, which is equal to 0.0198 meter or 19.8 millimeters. So that is how you solve for the elastic settlement of the soil. The next type of consolidation settlement is the primary consolidation settlement, which is very common in the settlement of clay layer. So in primary consolidation settlement, we have to first determine if the soil is a normally consolidated clay or over consolidated clay. So if the current effective stress is equal to the pre-consolidation stress, then the deposit is said to be normally consolidated. If the current effective stress is less than the pre-consolidation stress, then the soil is said to be over-consolidated. To explain further, halimbawa, ang lupa natin, di ba, ay may factors na nagabago-bago ang effective stress at a certain point. So, if the effective stress of soil is said to be less than the former effective stress na naranasan ng lupang yun. So, the soil will be over-consolidated. So, paano ba nagabago yung effective stress ng lupa? 'Di ba? Dahil one factor is the location of the groundwater table. So, yung groundwater table natin is laking epekto sa effective stress ng lupa. So kapag daw yung dating effective stress ng lupa ay mas mataas kesa sa effective stress niya ngayon, so over-consolidated yung lupa. Pero kung mas mababa naman yung effective stress na dati at yung current niya, yung pinakamataas na naranasang effective stress ng lupa at a certain point. So that would be normally consolidated clay. So that is the difference between normally consolidated and over-consolidated clay. So in normally consolidated clay, the formula is equal to C sub C H over 1 plus EO logarithm of sigma O plus change in sigma over sigma O. Or what does that mean? C sub C is what we call the compression index. H is the height of the clay layer. And E sub O is the original void ratio of the soil before consolidation. And this will be the sigma O is the effective stress or the overburden pressure of the soil at the mid-height of the clay layer, and the change in sigma is the change in stress due to application of load in the soil and therefore resulting to consolidation. And again, this will be the overburden pressure at the mid-height of the clay layer or the effective stress at the mid-height of the clay layer. So if it's over-consolidated, there are two situations. When P sub F is less than PC, what do you mean by P sub F and P sub C? So P sub F is the final stress, the summation of the overburden pressure plus the change in stress due to the application of load. And P sub C is the pre-consolidation stress or the pre-consolidation pressure. So if this will be the case, S sub C is equal to C sub S or the swell index multiplied by H over 1 plus the initial void ratio of the soil logarithm of the overburden pressure plus the change in stress over the overburden pressure. In the second situation, when P sub F is greater than P sub C or the final effective stress, which is equal to the overburden pressure plus the change in stress, and P sub C is the pre-consolidation pressure. So S sub C will be equal to C sub S swell index multiplied by H over 1 plus EO, logarithm of the pre-consolidation pressure over the overburden pressure at the mid-height of the clay layer plus the compression index multiplied by the height of the clay layer over 1 plus the initial void ratio, logarithm of the overburden pressure plus the change in stress over the pre-consolidation pressure. So the difference between the over-consolidated clay and the normally consolidated clay, again, the normally consolidated clay is whose present effective overburden pressure is the maximum pressure that the soil was subjected to in the past. And overconsolidated clay is whose present effective overburden pressure is less than that which the soil experienced in the past. The maximum effective past pressure is called the pre-consolidation pressure. Okay, so I've already explained the difference between the two earlier, so this is just an additional elaboration. So in compression index, so there are certain experts that study the compression index of clays. So according to Skempton, in order for us to determine the compression index of the soil, it is equal to 0.009 multiplied by the liquid limit minus 10. So this is the one usually used in calculation of the compression index. According to Rendon Herrero in 1983, C sub C or the compression index is equal to 0.141 multiplied by the specific gravity raised to 1.2 multiplied by 1 plus initial void ratio over the specific gravity raised to 2.38. And then we also have, according to Nagaraj and Morty in 1985, he determine the formula for the compression index, which is equal to 0.2343 multiplied by the liquid limit in percent over 400 multiplied by the specific gravity. So, also, by Roth and Wood in 1978, he determined the formula for the compression index, and it is approximately equal to zero point 0.5 multiplied by the specific gravity multiplied by the plasticity index in percent over 100. And according to Kulhawahi and Bain, in 1990, C sub C is approximately equal to Pi over 74. And then by Parr and Komoto in 2004, C sub C is equal to the initial porosity, which is N sub O, over 371.747 minus 4.475 minus the initial porosity of the soil before consolidation. Class, before they determine these formulas, they tested several types of clay, and it made them uh, conduct experiments a lot. So in compression index, there is a correlation. So these are the equation. There is also addition. So if it's remolded clay, you use Skempton. By if it's Chicago clay, you use this formula. And then all clays in organic cohesive soil, depending on the type of clay, you could use this formula. But mostly we use Skempton's formula, which is 0.007 times LL minus 10. But if in this case, in Skempton, he was also in revolved clay. So by Swell Index, which is C sub S, mostly we use C sub S as approximately about 1/5 to 1/10 cc. And Nagaraj and Morty also studied the swell index of the soil, and according to them, C sub S can be calculated with 0.0463 multiplied by the liquid limit in percent over 100 multiplied by the specific gravity. And by Kolwahi and Main, they also studied the swell index of the soil, and according to them, it's approximately equal to Pi, or the plasticity index of the soil, all over 370. So let us solve for primary consolidation settlement problem here. So in order for us to understand more of primary consolidation, let us consider this sample problem. So this is the figure, and from the figure shows the soil profile with the corresponding properties. The soil is acted upon by a uniformly distributed load of 60 kPa at the ground surface. So this 60 kPa is the additional load, and this is the cause of the settlement of this clay layer. So we are to compute for the settlement of the clay layer caused by primary consolidation if the soil is normally consolidated, and the settlement of the clay layer caused by primary consolidation if the pre-consolidation pressure of the clay is equal to 230 kPa, and we have to use the swell index is equal to 1/5 cc. And lastly, we have to compute the settlement of the clay layer caused by primary consolidation if the pre-consolidation pressure is 200 kPa. So let us solve the problem. So in the first unknown, we have to know the settlement of clay if it's normally consolidated. So the formula of the primary consolidation settlement is equal to C sub C H over 1 plus E logarithm of overburden pressure plus change in stress over the overburden pressure. So the C sub C is solved using the formula 0.09 multiplied by LL minus 10. This is the one usually used in order for us decompression index. And by substituting the values in the formula, 0.009 multiplied by 48 minus 10, this will be equal to 0.342. And then H is the height of the clay layer. So the height of the clay layer in this problem is 6 meters. So we are to use 6 meters in here. And E is 0.85. So the one we have to determine is the overburden pressure because it's not yet given. The change in stress is the change in P here, the 60 kPa. So this was the additional load. So how are we going to solve for the overburden pressure or the effective stress at the mid-height of the clay layer? So we have to determine the effective stress at the mid-height of the clay layer. That would be the overburden pressure. So the unit weight of this soil is given, the unit weight of the soil is given, and the unit weight of the soil is already given. So we just have to compute the overburden pressure. So in order for us to determine the overburden pressure, that would be equal to 16.5 multiplied by 4 plus this is already saturated because the groundwater table is located in here. So in order for us to determine the effective stress, we need to get the buoyant unit weight. So kahit hindi na tayo kumuha ng total stress at saka pore water pressure, we just have to get this buoyant unit weight of soil. That would be 18 minus 9.81 para hindi na tayo kumuha ng total stress at pore water pressure. Idiretso na natin ang pagkuha ng effective stress. And this will be the buoyant unit weight of the soil. So the saturated unit weight minus the unit weight of water is equal to the buoyant unit weight of the soil. Therefore, 18 minus 9.81 multiplied by 8 is equal to the effective stress until this point. So we have to get the effective stress at this point. Plus, this buoyant unit weight of this soil, we have given saturated unit weight. So that's why we just have to subtract 9.81 from 20 in order for us to get the buoyant unit weight. And then multiply it by 3 because we have to determine the stress at the mid-height of the clay layer, which is 3. So this will give us the value of the overburden pressure at the mid-height of the clay layer. This will be equal to 162.09 kPa. So we already have all the values in order for us to determine the settlement of the clay. So by substituting, this will give us 0.342, the compression index of the soil, which we already solved earlier, multiplied by the height of the clay layer, which is equal to 6, over 1 plus the initial void ratio is 0.85, logarithm of the overburden pressure, 162.09, plus the additional load, which is 60 over 162.09. I'm sorry, that should be just 162.09. We have to omit this one. So 162.09, and this will give us the value of the settlement of the soil if it's normally consolidated. This will be equal to 0.152 meter or 152 mm. Next, we have to determine the settlement of the clay if there is a pre-consolidation pressure, if it's over-consolidated. So the pre-consolidation pressure, that means that this is the maximum effective stress that the soil has been subjected into. So we have to first determine if PF is less than or greater than P sub C. So we have to determine the PF. So PF is equal to the overburden pressure plus the additional load. So this will be 162.06 plus 60. This is 222.09 kPa all in all. And 222.09 kPa is less than 230 kPa. Therefore, PF is less than P sub C. So if PF is less than P sub C, the formula for the primary consolidation settlement is equal to C sub S, which is the swell index, multiplied by the height of the clay layer all over 1 plus E, logarithm of overburden pressure plus additional load over the overburden pressure at the mid-height of the clay layer. So in this case, C sub S is not given. But in the problem, there is a note that C sub S should be equal to 1/5 of the compression index, and 1/5 of the compression index, which is equal to 0.342, is equal to 0.068. So by substituting again the values, because we already have the value of C sub S, and then H, E, and then this stresses, this will give us 0.068 multiplied by 6 over 1 plus 0.85, logarithm of 162.09 plus 60 over 162.09. The primary consolidation settlement of the soil if P sub C is equal to 230 kPa. is equal to 0.030 meter or 30 millimeters. And then lastly, we have to determine the settlement of clay if the pre-consolidation pressure is 200 kPa. Again, in order for us to determine the primary consolidation settlement if it's over consolidated clay, we have to again compare PF and PC. So by comparing PF and PC, the PF is equal to 162.06 plus 60 and 222.09 kPa is greater than 230 kPa. So if PF is greater than P sub C, therefore, the formula for primary consolidation settlement of the soil will be equal to C sub SH over 1 plus EO logarithm of the pre-consolidation pressure over the overburden pressure plus the compression index multiplied by the height of the clay layer over 1 plus EO logarithm of the overburden pressure plus the additional load over the pre-consolidation pressure. So we have given swell index, we have given height of the clay layer, void ratio is already given, pre-consolidation pressure is given, overburden pressure was already solved, and the additional load is 60 kPa. So we just have to substitute the values in the formula, and this will give us 0.068 times 6 over 1 plus 0.85 logarithm of 200 over 162.09 plus 0.342 multiplied by 6 over 1 plus 0.85 logarithm of 162.09 plus 60 over 200. The value of the primary consolidation settlement if PC is equal to 200 kPa is equal to 0.071 meters or 71 millimeters. And that would be the answer for the sample problem regarding primary consolidation settlement. The next factor that we have to consider in consolidation settlement is the time rate of consolidation. As we all know, the consolidation settlement of clay layer takes time. So, at a certain period of time, hindi agad-agad ma-achieve nung lupa yung kanyang 100% settlement. So, we consider time rate of consolidation in order for us to know the certain time kung kailan makukuha nung lupa yung kanyang 100% settlement. So, in time rate of consolidation, we have to consider the time factor, which is equal to C sub V multiplied by T over HDR squared, where C sub V is constant and HDR depends on two situations. So the HDR will just be one half of the thickness of the drainage layer if drainage occurs at the top and bottom of the clay layer. And it will be the thickness or the whole thickness of the clay layer if drainage occurs at the top or bottom only or a one-way drainage. So if this is the case, the one-way drainage is like this one. If this is if this is the clay layer and this layers are both permeable layers. So magde-drain siya dito, mag-aalis ng tubig dito. Aalpas din ang tubig dito due to application of load. And that would be the two-way drainage. And HDR in this situation will just be half of the thickness of the clay layer. And then, if this is the case, this will be one-way drainage. Ito lang yung permeable. Impermeable na yung baba ng clay layer na ito. So, yung expulsion ng tubig ay dito lamang mangyayari kapag nag-apply ng load sa taas lamang. So, this will be just one-way drainage. Also, In this case, if this is the only permeable layer and the top layer of the soil or clay layer here is impermeable, and this is just the one permeable layer, this will just be one-way drainage. And if it's one-way drainage, you just consider the whole thickness of the clay layer. So in order for us to determine the percentage in with respect to time factor, so we have to consider this formula. For U is equal to 0 to 60%, the time factor is equal to pi over 4 multiplied by the percentage over 100 square. And if it's greater than 60, TV is equal to 1.781 minus 0.933 logarithm of 100 minus U percent. What is U? The percentage nung settlement na na-achieve ng lupa. So, Sivaram and Swami in 1977 gave the following equation for variation of U from 0 to 100%, and this is given in this formula. And there is a table in order to determine T sub B para hindi na mag-solve, and this is the one we usually use. So TV at a certain percentage of settlement is already given in this table. So the time rate of consolidation, and we have decompression index. In time rate of consolidation, we use the compression index is equal to E sub 1 minus E sub 2 over logarithm of P2 over P1, which is the void ratio at P sub 1 and E sub 2 is the void ratio at P sub 2. So this is the one used in laboratory. If we have pressure 1, and this will be the void ratio at pressure 1, and then we apply load again at the soil sample, and the void ratio will change again. This will be E sub 2, and the pressure applied at E sub 2 is P sub 2. The coefficient of compressibility is the ratio between the change in void ratio and the change in effective stress for the given increment. And A sub V is the coefficient of compressibility, which is usually expressed in meter squared over kilonewton. The formula for coefficient of compressibility is equal to E sub 1 minus E sub 2 over P sub 2 minus this will be P sub 1, not P sub 2. Also, we have what we call the coefficient of volume compressibility, which is MV. It's equal to E1 minus E2 over 1 plus E average, the average of these two void ratios, multiplied by P sub 2 minus P sub 1. And this is the average void ratio. This will be equal to A sub V over 1 plus E average, because we all know that this is A sub V or coefficient of compressibility. And then we have coefficient of consolidation, which is equal to the hydraulic conductivity of the soil over the volume compressibility multiplied by the unit weight of water. So let us again solve problems in order for us to understand more of time rate of consolidation. So under a given surcharge, a 5-meter thick clay layer has a consolidation settlement of 300 millimeters. So we assume that the constant CV is equal to 0.003 centimeters squared per second. And what will be the average degree of consolidation for the clay layer when the settlement is 75 millimeters, and how long will it take for 50% consolidation to occur if the layer is drained on the top only. And lastly, how long will it take for 50% consolidation to occur if the layer is drained on both sides? So In order for us to determine the average degree of consolidation for clay layer when the settlement is 75 millimeters, we have to determine the percentage. So the settlement is 75 millimeters, but the overall settlement of the clay layer should be 305 millimeters. So 75 is just how many percent of 305 mm? So 375 over 305 is equal to 0.2459 or 24.59%. So at 75 mm, the percentage of settlement of clay is just at 24.59%. The soil has just achieved 24.59% consolidation settlement. And then, how long will it take for 50% consolidation to occur if the clay layer is drained at the top only? So we all already know that the formula for TV is equal to H, CVT over HDR squared. So we need to know the time. So in this case, time is equal to T sub V or the time factor multiplied by HDR squared over CV. So TV, how are we going to get T sub V or the time factor? This is 50% consolidation. So from the table, we get the value of T sub V and the time factor at 50% consolidation from the table is equal to 0.197. So therefore T sub V here is 0.197. HDR is drained at the top only. So if it's drained at the top only, it will be one-way drainage. And HDR, if one-way drainage, is the whole thickness of the clay layer, which is 5 meters. And C sub V is given. So 0.197 multiplied by 5 meters or 500 squared because C sub B is in centimeters. So we convert 5 meters to centimeters here over 0.0.003. This will give us time in seconds. 16,416,667 seconds converted to days is equal to 190 days. And then lastly, we have to determine how long will it take for 50% consolidation to occur if the clay layer is drained on both sides. So, ang magbabago lang dito is the HDR. Time factor is still 0.197 and C sub V or constant is equal to 0.003 centimeters squared per second. So, let us substitute 0.197, the half of the thickness of the clay layer is 250 centimeters squared over 0.003. And this will give us 4,104,167 seconds. Converted to days is equal to 47.5 days. Next problem. Under a normal loading condition, a 3.6 meter thick clay, normally consolidated, has PO, which is equal to 190 kPa, and E sub O, which is equal to 1.22. So the origin at the initial pressure given is 190 kPa. At 190 kPa, the void ratio of the soil is 1.22. A surcharge of 190 kPa reduces its void ratio to 0.98. The hydraulic conductivity of the clay for the loading range is 6.1 times 10 raised to negative 5 meters per day. So what is the coefficient of the volume compressibility of the clay? What is the coefficient of consolidation of the clay? And how long will it take for this clay to reach 60% consolidation if it is drained on one side only? So in order for us to solve for A, the coefficient of volume compressibility is equal to mv. So the coefficient of compressibility is equal to E sub O minus E over change in P, or P2 minus P1. So 190 plus 190 is 380. So dinagdagan kasi ng 190 yung initial pressure. That's why this will just be the change in pressure na. This will not be P1 P2 minus P1. This will just be change in P, which is 190, over the 1 plus average void ratio. So 1.22 minus 0.98 over 190 over 1 plus 1.22 plus 0.98 over 2. This will give us the value of the coefficient of volume compressibility, which is equal to 0.006015 meters squared per kilonewton. So for letter B, we have to get the CV, or coefficient of consolidation. It's equal to the hydraulic conductivity over MV multiplied by the unit weight of water. So the hydraulic conductivity of the soil is given as 6.1 times 10 raised to negative 5 over MV is already solved as 0.006015 multiplied by the unit weight of water. This will give us the value of CV, which is equal to 0.01034 meters squared per day. And lastly, we have to determine the time for the clay layer to reach 60% consolidation if it is drained on one side only. So the time factor at 60% is equal to 0.286 from the table. So this will be used in the formula for T. HDR should be the whole thickness layer because it is drained on one side only. That's why this will be one-way drainage. And substituting the value, this will give us 0.286 multiplied by 3.6 squared over the value of coefficient of consolidation. This will be 0.01034. And the time in order for the clay to reach 60% consolidation in one-way drainage is 358.5 days. Next problem. So this is an example of settlement due to additional load by footing. So the footing shown in the figure supports a load of 224 kilonewton, including the weight of the footing, and the footing is 1.5 meter by 1.5 meter plan. So we have to determine the settlement of the soft clay, the number of days for the consolidation of clay to reach 80%, and the settlement after 20 days. So how are we going to solve for the settlement of the soft clay? So in this case, there's now given influence factor or anything about elastic settlement. So it was not mentioned that the footing was has elastic settlement. I mean the clay has had elastic settlement due to the footing. So none. So therefore, we have to solve for the primary consolidation settlement. So in primary consolidation settlement, it's equal to C sub C over H over 1 plus E logarithm of overburden pressure plus change in the effective stress plus overburden pressure. So why do we need to use this formula? It's not mentioned that it's over consolidated. So automatic, it's normally consolidated clay. There's no given pre-consolidation pressure. So automatic, it's a normally consolidated claim. CC is given, H is 1.2 meters, but E is not given. If I overburden pressure at the mid-height of the clay layer is not given, so we have to solve it. And the change in stress is still we have to know what is the value. So, in order for us to get the void ratio, it is given that the moisture content is 22%, that is percent, and the specific gravity is 2.60. We all know from the relationship between the four properties, the degree of saturation, the void ratio, the moisture content, and the specific gravity. If it's saturated soil, S is equal to 1. So SE is equal to MCGS or WGS. But because S is equal to 1, because it's saturated and it's under the water table, S is equal to 1. So E is equal to the moisture content multiplied by the specific gravity. So it will be equal to 0.22 multiplied by 2.60. It's equal to 0.572. And then, in order for us to get the overburden pressure at the mid-height of the clay layer, so the until this one, at this point, point 6 from here, this will be 9.60, 19.6 rather, multiplied by 1.2, plus the buoyant unit weight of this soil is equal to the saturated unit weight minus the unit weight of water. So 18 minus 9.81 multiplied by 1.2. And then lastly, the buoyant unit weight of this soil is 16.5 minus 9.81 rather, multiplied by the mid height of the clay layer is zero point 0.6. Therefore, the overburden pressure at the mid height of the clay layer is 37.36 kPa. So we already know CCH1 plus E logarithm, E and the overburden pressure, we have to know what is the value of the change in stress. Will it be just equal to 224? Actually, the answer is no. Why? So if it's a footing, the change in stress is equal to the change in stress at the top, the change in stress at the mid height of the clay layer, and the change in stress at the bottom of the clay layer all over 6. So if it's a footing, we need to consider na yung change in stress dito is 224 din. Kapag siya ay footing, from this table, from this surface rather of the footing, habang nababa siya, yung application ng load, yung epekto ng pag-apply ng load natin sa footing, ay naliit pababa. Habang yung nararamdamang stress ng lupa due to this application of load, naliit siya pababa. Kasi yung area of distribution ng stress na 224 kilonewton, habang nababa ay nalaki yung area of distribution. So, in in footing, we consider the trapezoidal method. And usually, ang distribution daw ng ating load is about 1:2. So, paano yung 1:2? We have to determine yung area of distribution sa top ng clay layer natin, sa mid-height ng clay layer natin, at yung bottom ng clay layer natin. Ano yung 1:2 method? Diba, ito is 1.5. So, sabi dun sa problem, 1.5 meter by 1.5 meter daw yung ating footing. So, if it's 1.5, habang nababa siya, this will still be 1.5, diba, yung gitna, 1.5. Pero habang nababa, diba, from this bottom of the footing, if this is 1.8, 1.8 yan, from the bottom of the footing, 0.6 plus 1.2. Ito yung top ng footing natin, di ba? I mean, top ng clay layer. So, this will be 1.8. If this is 1.8, and we consider 1:2 method. So, by 1:2 method, kung ito ay 2, yung ating vertical, yung horizontal natin ay 1. So, 1.8 divided by 2 is equal to 0.9. Kaya makaka-form tayo ng triangle dyan, which is 0.9. At meron din dyan na triangle na ito, kung ito ay 1.8 and 1:2 method siya, 0.9 itong nasa baba. So therefore, yung area of distribution ng ating lupa ay ng ating load is 1.5 plus 0.9 plus 0.9, it's equal to 3.3. So, magiging square yan. Magkakaroon din yan ng yung kabila din natin, pag nag-drawing tayo, ganyan yan, ganyan, dun sa kabila. In 3D, ganyan yan. So, this will be 1.5 plus 0.9 plus 0.9. This will be 3.3. Yung kabila din is 3.3. And therefore, pag in-applyan natin siya ng load na 224 kilonewton, so 224 over 3.3 times 3.3, this will be the stress. So 224 over 3.3 squared is 20.57 kPa. And then, at the mid-height of the clay layer, also, ganun din. So, erase tayo. At the mid-height of the clay layer, hanggang mid-height ng clay layer natin ay ilan? 0.6 plus 1.2 is already 1.8 plus 0.6 is 2.4. So if it's 2.4, itong height na ito, 2.4, ito ay magiging 1.2. If it's 2.4, this will be 1.2. Yung gitna, 1.5. So 1.2 plus 1.5 plus 1.2, this will be 3.9. So the area of distribution, again, of the load, which is 224 kilonewton, is 3.9 by 3.9. So, para makuha yung stress, force over area is equal to stress. So, 224 over 3.9 squared is 14.73 kPa. And lastly, at the bottom ng clay layer is 0.6 plus 1.2 plus 1.2 is equal to 3.0. Am I correct? So, kung 3.0 ito, yung height, ito ay magiging 1.5 due to 1:2 method. Kung ito ay 3.0, ang kalahati ng 3.0 is 1.5. So, the area of distribution will be 1.5 plus 1.5 plus 1.5. The bottom will be 4.5 meters square. And the area of distribution the area of distribution will be 4.5 by 4.5. So the stress at the bottom is 224 over 4.5 squared, and it will be equal to 11.06 kPa. So to determine the change in stress due to this load at the footing, it's equal to the change in stress at the top plus 4 mid plus change in stress at the bottom over 6. By substituting these values to the formula, this will give us 20.57 plus 4 multiplied by 14.73 plus 11.06 over 6. This is adapted from the Presmoidal formula if you still remember your surveying classes. So, dito din yun yung Presmoidal formula natin. And this is equal to 15.09 kPa. So, we already solved for the values again. In order for us to determine the settlement, it's equal to CCH over 1 plus E logarithm of overburden pressure plus change in stress over overburden pressure. CC is given, everything is given. So we just have to substitute 0.32 multiplied by the height of the clay layers 1.2 over 1 plus 0.572 logarithm of 37.36 plus 15.09 over 37.36 SC or the primary consolidation settlement is equal to 0.03599 meters or 35.99 millimeters. And then for letter B, we have to determine the number of days for the consolidation of the clay to reach 80%. So again, we determine the time using the formula TV multiplied by HDR squared over CV. So in this case, how do we know that it's one-way drainage or two-way drainage? So you look at the layers at the top and the bottom of the clay layer. So this is sand and this is dense sand. But we all know that sands are permeable. Therefore, magkakaroon ng expulsion ng tubig dito at magkakaroon ng expulsion ng tubig din doon sa bottom kapag nag-apply ng load. So therefore, this will be two-way drainage. And if you were consider the HDR will be equal to half of the thickness of the clay layer, which is equal to half of 1.2 is 0.6 meters. Therefore, HDE, TV rather, in if U in percent, if it's 80% consolidation, from the table is 0.567. Therefore, 0.567 multiplied by 0.6 squared over CV is given 6.5 times 10 raised to negative 3 meters squared per day. This will give us 31.40 days in order for us to reach 80% consolidation. In order for the clay to reach 80% consolidation. And lastly, the settlement of the clay after 20 days. So, again, we consider this formula. T is equal to time factor HDR squared over CV. So, in this case, 20 days or the time is given. But we don't know the time factor at 20 days because we don't know the percentage of consolidation at 20 days. So we need to determine this first. HDR is already the half of the thickness of the clay layer because we already analyzed the soil and we have seen that this will have two-way drainage and CV is already given. So the only thing unknown in this formula is the time factor or TB. So TV or 20 is equal to TV multiplied by 0.6 squared over 6.5 times 10 raised to negative 3. TV is equal to 0.361. So we have to determine What is the percentage of consolidation if the time factor is 0.361? So let us look at the table. Where is 0.361 located? If we look at the table, 0.361 is between 0.352 and 0.364. So how are we going to determine the percent consolidation? Would it be 66% or will it be 67%? So we have to consider, hindi pa na-reach nung lupa yung kanyang 67% consolidation dahil 0.361 pa lang siya. Ibig sabihin, 66% pa lang ng consolidation yung na-achieve ng lupa. Hindi pa siya naabot ng 0.364 yung TV. Therefore, the percent consolidation is equal to 66%. So how are we going to determine the settlement after 20 days? We already solved for the settlement of the clay layer. At we already solved that it's equal to 35.99. So the 66% of 35.99 is equal to 23.75 mm. And that is the settlement of the clay after 20 days. And that is the sample problem regarding time rate of consolidation. Let us now move on to secondary consolidation settlement. So where we have to get the formulas for secondary consolidation settlement. And the formula for secondary settlement is equal to, we need to first know the compression index or the secondary compression index. So the secondary compression index is equal to change in E over logarithm of T sub 2 minus logarithm of T sub 1. Or equal to change in E over logarithm of T sub 2 over T1. Where C alpha is the secondary compression index. Change in E is the change of void ratio. T sub 1 and T sub 2 are the time. And the magnitude of the secondary consolidation can be calculated as C prime alpha H logarithm of T sub 2 over T sub 1, where C prime alpha is equal to the secondary compression index or C alpha over 1 plus EP. What is EP? It's the initial void ratio at the end of primary consolidation, or EO minus change in E. And H is the thickness of the clay layer. Or we can also solve for change in E, which is equal to CC logarithm of overburden pressure plus change in effective stress over the overburden pressure. Let us solve some problem in order for us to understand more of the secondary consolidation. So this is a sample problem regarding secondary consolidation. This is the soil formation, and it has a groundwater table located at 2 meters below the ground surface. And the ground surface is subjected to a uniformly distributed load of 40 kPa. So we need to first get the primary compression index, the primary consolidation settlement of the if the clay is normally consolidated, and lastly, we have to compute the secondary consolidation settlement of the clay layer after 5 years after the completion of primary consolidation settlement. Time for completion of primary settlement is 1.5 years. So therefore, 5 years plus 1.5 years. So we are at the 6.5 year na. And the secondary compression index is C alpha equals 0.02. So we need to determine first the primary compression index. So the primary compression index is equal to C sub C is equal to 0.009 multiplied by LL minus 10. Given the liquid limit, the liquidity index and the plasticity index in this formula. Another plastic limit rather. So its plasticity index, liquidity index is equal to moisture content minus plasticity limit over LL minus PL. 0.64 is equal to 40 minus 20 over LL minus 20. Therefore, this will give us LL, which is equal to 51.25. And substituting the value, this will give us 0.009 times 51.25 minus 10. The primary compression index is equal to 0.371. Next, we have to determine the primary consolidation settlement. So the soil is a normally consolidated clay. So therefore, it's equal to CCH over 1 plus E logarithm of sigma O over plus plus change in sigma over sigma O or the overburden pressure. So how are we going to solve for the overburden pressure? In this case, the only unit weight given is the unit weight of the sand in here, the dry sand, and then the saturated sand. But the unit weight of the clay is not yet given. So we have to first get the unit weight of the clay layer. So the unit weight of the clay layer, because it's under the groundwater table, is saturated. So it's equal to specific gravity plus E over 1 plus E multiplied by the unit weight of water. Therefore, it's equal to 2.6 plus zero point 0.6 over 1.6 multiplied by 9.81. The saturated unit weight of the soil is 19.62 kilonewton per square meters. So now we can get the overburden pressure at the mid height of the clay layer, so that would be 2.5 and 17.66 times 2 plus the buoyant unit weight of this soil is equal to 20.93 minus 9.81 multiplied by 3 plus the buoyant unit weight of this soil is 19.62 minus 9.81 multiplied by 2.5 because we just have to consider the overburden pressure at the mid-height of the clay layer. So that would be 2.5. And the overburden pressure at the mid-height of the clay layer is 93.13 kPa. So therefore, the primary consolidation is equal to 0.371 multiplied by 5 over 1 plus zero point 0.6 logarithm of 93.13 plus additional load is 40 kPa over 93.13. So the primary consolidation settlement is equal to 0.180 meters or 180 millimeters. And then lastly, we have to determine the secondary consolidation settlement after the completion of primary settlement 5 years after. And the secondary consolidation settlement is equal to C alpha H over 1 plus EO or EP logarithm of T2 over T1. Or rather, it's EP, not EO. So the void ratio at the end of primary consolidation is equal to the initial void ratio of the soil minus change in E. And in order for us to get the change in E is equal to CC logarithm of the overburden pressure plus the additional stress over the overburden pressure. So CC is 0.371 logarithm of 93.13 plus 40 over 93.13. So therefore, the change in E is equal to 0.058. So the void ratio at the end of primary consolidation is equal to 0.60 minus 0.058. It's equal to 0.542. Therefore, the secondary consolidation settlement is equal to 0.02 multiplied by 5 over 1 plus 0.542 logarithm of the first the time after completion of primary settlement is 5 years, and the time for completion of primary consolidation is 1.5. Therefore, SS, or the secondary consolidation settlement, is 0.034 meter or 34 millimeters. Class, take note. You have to look at the problem. If the problem is determine the secondary consolidation settlement after 5 years. So, ibig sabihin, yung after 5 years na yun, hindi pa na nasusubtract yung kung gaano katagal yung primary consolidation settlement. Say for example, after 5 years, tapos it takes 1.5 years to for the primary consolidation settlement to occur. So, ang T2, T sub 2, ay yung years after primary consolidation settlement. So, pag ang sabi is secondary consolidation settlement after 5 years, so ibig sabihin, isa-subtract mo muna yung time na nag-take yung primary consolidation settlement. Ibig sabihin, 1.5, 5 minus 1.5 is 3.5. Kasi ito, yung 5 years dito is yung time lamang na nagasimula na yung secondary consolidation settlement. So, pag ang tanong is 5 years after, so, ibig sabihin, this will be 3.5 over 1.5. So, ito kasi is 5 years after completion of primary consolidation settlement. Okay, so that would be all for the compressibility of soil. And if you have questions, you may always contact me anytime and I will try to answer your questions. Thank you everyone, and I hope to see you all. Bye.